Well, hello geometers and seekers of general truths. In this video, we will discuss and prove the segment of chords theorem. And we've worked with this a little bit already in one of the examples, but now let's formalize it and let's see what this says here. If two chords intersect in the interior, so I have two chords, A, B is one of them, and D, C is the other chord, and they intersect at point E. Then the product of the lengths of the segments of one chord. So the product of the lengths means that if you're taking EA, that's this part of the chord, multiply it by EB, so EA times EB, is equal to the product of the lengths of the other chords. So EC, right, multiplied by ED. So if you take those four smaller segments, the two green ones multiplied together is equal to the yellow ones multiplied together, right? And so what I'm going to do is show you a proof of why this is true. And we've seen examples of this already, but we're going to do this with variables so that we show that this is true for all possible cases and numbers. All right, so I'm going to clean up the picture a little bit because I'm going to continue annotating. I don't want this getting too messy, but the idea here has been what's been highlighted. That's what we're trying to show. And if you recall, like in some of the previous problems, what we do is we're going to make triangles out of this, okay? And then we're going to try and show that these two triangles are in fact similar. And so what the first thing we can say is that these two angles here in the middle, they're vertical angles. So they have to be congruent to each other. AED and CEB are vertical angles, so they're congruent. Okay, and then we can lean on the inscribed angle theorem. And if we look at, let's look at angle B here, or angle ABC. Okay, it inscribes this arc AC, right? It inscribes this particular arc. So we know that it must be half of that arc measure. But by the same token, angle D, or ADC, inscribes the exact same arc. So let me draw this in here. So the blue angle here and the green angle intercepts the same arc, so they have to be equal to each other as well. All right, so you have two angles, ADE, that's the green one, and CBE, that's the blue one. They intercept the exact same arc, so they're both half of that arc, so they have to be equal to each other. Okay, and now that's it. Now let me put these marks in here. And now with that information, it is enough to say that the two triangles are similar to each other. Triangle ADE and triangle CBE. Okay, so that's the angle postulate. And since they're equal to each other, they're similar to each other, excuse me, we can set up a statement of proportionality. And we can say, look, EA, that's this segment right here, it must match up to EC. So we can say that EA over EC, that must be equal to another part of this that's proportional, which is ED, right? That's this segment right here. It connects these two congruent angles, so it must be proportional with this other line segment here that also connects those two congruent angles. So this is ED over EB. Okay? So this is a statement of proportionality. Then we cross multiply, and if you notice what happens when we cross multiply, EB times EA, that's what we have here, is equal to EC times ED, and that's what we have here, and that completes the proof. Okay, so hopefully you see here that there is this relationship here with the product of these lengths of the chords, and it's really helpful to solve the problem that way if you happen to have that memorized. But all of this really comes from the idea of triangles being similar to each other, that when two chords intersect inside of a circle, that we can make some other connections to produce similar triangles. And so I'm going to stop the proof here, As always, ask for help if you need it. Thank you for watching and have a wonderful day.